So, we've introduced the basics of probability. Hopefully basics doesn't sound condescending. I don't mean it to be. Anyway, as we've seen, probability calculations end up really depending on effectively counting how many different ways an event can occur. So, you probably recall we've done an awful lot of stuff already as far as counting is concerned in the first week of course. So yeah, we're going to call all that stuff in to help us calculate probabilities now. So in the PowerPoint slides I posted in Moodle, you'll find a convenient sort of recap of counting stuff, the fundamental counting principle, the permutation formula, the combination formula, when you need to use them. Just like before, you don't need to have those formulas like committed to memory. I assume you've got a calculator that'll work out 5p3 or 7c6 if you need it. So the big thing to remember is, as far as it goes, remember we count permutations when the order in which we choose things matters. If we don't care about the order of selection, then we're counting combinations. And then the other stuff, like I said, the base ideas, that's, I think something hopefully you'll recall. So anyway, let's take a look at this in the context of some examples here. So first off, your favorite musical artist has released a new album. Once upon a time, I would go look up whoever happens to be sitting at the top of the Billboard charts. These days, yeah, I'm comfortable enough in my old fogeyhood that I'll just listen to old Toto songs and say, fill in the blanks for whatever you think is cool. So, new album comes out. It's got 13 tracks on it. So, assume you're going on a trip somewhere, like, from Mars Hill to Asheville or something like that, and you've got a half hour of travel time. You're only going to be able to listen to 6 songs. So, you put your music player on shuffle, and it starts doing its thing. It's not going to repeat a song until it's played everything. So how likely is it that the last song you hear as you get out of your car is the favorite song of yours on the album? So we want to know how likely it is that your favorite song comes up last. So let's sketch out what we got to work with, and then we'll talk about the probability. So we've got 13 songs. We're going to pick 6 of them to play, and sort of by design, since we want to know if what we hear last is our favorite, this time around, the order in which we pick things is going to make a difference. So if we need to do something, we're going to want to use permutations rather than combinations. All right. So in terms of how we set this up, I'm going to start it off using our buddy, the fundamental counting principle. So we kind of have 6 slots to fill, the 6 songs we hear. So that's supposed to say first, but my handwriting is terrible. I give up. Yeah. All right. So now, when we've done this in the past, normally we kind of start from here and work our way back. You can do that here, but you've kind of got to take something into account first. The big thing is we actually know exactly what we want in this particular spot, the last song we hear. I've seen students sometimes set it up as actually working backwards from the 6th song to the first. That's okay if you do that. In any case, we have exactly one choice for what song we hear 6th in terms of how we want things to happen. All right, since our shuffle player isn't going to repeat stuff, that means we only have 12 of the 13 songs available to us at this spot. So we've got 12 right there. From here, it counts down just like we've seen previously. With no repeats, we're down to 11 tracks for the 2nd slot. 10, 9, 8. All right, at this point, our buddy, the fundamental counting principle, says we can just hook all those guys up with dots. And when I work out that multiplication, that gives me 95,040 ways this could end up happening. Okay? So, that's the number of ways it could happen, which sounds like a lot. The catch is, it's a probability. We got to divide this by the total number of possible ways our music player could pick out 6 songs without repetition. So this is like at the top of the fraction. So to the bottom, we need, well, we got 13 songs. I've already said it. We're picking out how many of them? That's right, 6. And our order matters. So we want to count permutations. I need a P right there. Okay. Now, you work this guy out, and you get a pretty beefy number. I got 235,520. That's a lot. Okay, so now if we want to work out the probability, we've got to divide this by this. So I'm just going to kind of cordon this off so you can see here. The probability that your favorite song plays last is 95,040 divided by that big million thing. So we've got that. I totally don't blame you if this is not a decimal that you're comfortable just leaving around. I mean, you can reduce it a bit if you'd like. I mean, it turns out it breaks down pretty conveniently. But when I work this out as a decimal, I got 0.0769. So there's a little more than a 7.5% chance that this is what ends up happening. Okay? So that's one way we could do this. There's actually a second way you could calculate this that doesn't end up calling in the counting principle, because you may notice, since this guy's locked into place, all we really needed to do was pick out the 12 songs, or pick out the 5 songs, rather, from the other 12 that play in front of it. So alternatively, you could have done it like this. You just take permutations of 5 songs pulled out of the set of 12 that you had, and lo and behold, that works out to be, again, 95,040. So 2 ways to get the same problem. Okay? 1 problem down. All right. Let's take a look at some more examples here. So the next kind of battery of examples I have to pick from are all kind of drawing from the same well, and it sounds kind of familiar. Imagine we've got some like upper level class, so you're taking a higher level management course or something like that. You've got 14 students on roll. So we have 14 students in the class. 6 of them are juniors academically, and 8 of them are seniors. Okay? So the professor is going to pick out a pair of students to work together on the project. So now, no particular roles are being assigned here, so in this instance, I'm going to say the order in which a student gets picked doesn't make a difference. So we got to pick out 2 students from the group. Okay. So the first thing I want to look at is, how likely is it that our group, well, I say group, it's really a pair, right, is both seniors? All right. Now, again, we could set this up kind of in broader strokes. I usually have a lot more like flowery sentences around this, but I don't have a ton of space. Is what we're going with. So we got a fraction. That part we're hopefully used to. On the top of this thing, I need the number of ways I could pick out 2 seniors from my group. Well, I have 8. I'm picking out 2, and the order of selection doesn't matter. So that's going to look like 8C2. Down below, I've got to count the total number of ways our professor could pick 2 students from the entire class. So we're still picking out 2, but now we're drawing from the full pool of 14 in the bottom of the fraction. So it looks like 8C2 over 14C2. So when I worked these guys out, I got up top 28. Down below, I got 91. This fraction actually, trims up a bit because both of those guys are divisible by 7, so you can cut your answer down to 4/13 in this case. Okay, all seniors. Let's take a look at what happens if we wanted to get only juniors for some reason or another. So the only thing that really changes inside this guy is I'm going to have juniors. Okay. As far as the actual probability fraction goes, not a lot adjusts here. The bottom is still going to be 14C2. That we haven't changed the enrollment of the class at large. The only thing that's going to adjust is this one thing right here, because now instead of picking out from the 8 seniors, we got to pick out from 6 juniors. Okay? Can't erase cleanly. All right, so we have 6C2. So the bottom is still 91, the 4/13 it can go away. When I worked out 6C2, I got 15. All right, so this doesn't really reduce. Again, if you wanted a decimal, that's okay. I get it. So yeah, so we've got the probability we pick out both seniors, probability we pick out both juniors. So lastly, what if we want to split? Maybe the professor is trying to avoid senioritis totally kicking in on somebody and messing up their final project. So again, I don't need to change a ton here. So still a fraction. The denominator is still going to be 14C2. We got to dig in a bit though here because we technically have two separate choices we need to make. We got to pick one junior, we've got to pick one senior. So you could write that out using combinations like 6C1, 8C1, and then use the counting principle to multiply them together. You may just end up saying, well, why don't we just do 6 times 8 for picking the junior, then picking the senior? If you do, I get it. That's what I'd have done. And then we get 48 up top. We still got that 91 down below, and that's that. So, all right. I'm going to keep playing around with this example in the next video. I'm just going to ramp things up a bit instead of it being a group of 2. So keep on watching, and you'll get to see some more variations on the theme.